Hello friends, today I would like to share with you the topic atomic structure. In that, the first topic is particles in the atom and atomic radius. So let's see the details. Every substance in our world is made up from chemical elements. As we know, every element has its own chemical symbol, and most of the symbols are derived from Latin or Greek words. Here some examples are shown. Carbon symbol is C, lithium Li from the Greek word lithos, iron Fe from Latin ferrum, potassium K from Arabic alquilia or from Latin kalium. So this is how each and every element is getting the symbol. And what do you mean by an element? An element is a substance containing only one type of atom. And what do you mean by an atom? An atom is the smallest part of an element that can take part in a chemical change. These are the subatomic particles inside an atom. Proton is a positively charged particle inside the nucleus of the atom. Neutron, uncharged particle inside the nucleus of an atom with the same relative mass as a proton. And the electrons are the negatively charged particles found in orbitals outside the nucleus of an atom. It has negligible mass compared with a proton. All the atoms in an element have the same proton number. Every atom contains protons in its nucleus and electrons outside the nucleus. Most atoms have neutrons in the nucleus except isotope of hydrogen. And we call the sum of protons and neutrons as a particular number. That's called the mass number. Otherwise, it's also called the nucleon number. So the number of protons plus neutrons is the nucleon number. These are the particles seen inside the nucleons. That's why it's called nucleon number. And this is giving you the details of the masses and charges of the subatomic particles. Subatomic particle, electron symbol is E and relative mass 1/1836, relative charge -1. Neutron symbol N, relative mass 1, charge 0. Proton symbol is P, relative mass 1, relative charge +1. Now we are going to see how the subatomic particles behave in an electric field. So this is a picture demonstrating the effect of electric fields on the beams of proton, neutron and electron. So as you can see here, the electric field is shown as plus and minus charge, and the beams have been passed through this. Neutrons are traveling in a straight line. As you can see, no deflection at all because neutron has no charge. But the proton and electrons gets deflected. The electron deflected more than proton as it has a smaller mass than proton. That's why lighter the mass, so it can deflect more. Heavier, deflection will be lesser. That's what's shown in the picture. Protons, neutrons and electrons behave differently when they move at the same velocity in an electric field. That's what we have seen now. When a beam of electrons is fired past the electrically charged plates, electrons are deflected very easily away from the negative plate towards a positive plate. This proves that electrons are negatively charged. Like charges repel each other, it also shows that electrons have a very small mass and they are easily deflected. A beam of protons is deflected away from the positive plate and towards the negative plate. This proves that the proton is positively charged. As protons are deflected less than electrons, this also shows that protons are heavier than electrons. A beam of neutrons is not deflected at all, which proves that the particle is neutral in nature. It's not attracted to or repelled by the negative or positive plate. So these are the evidences from the picture which we have seen. In a neutral atom, the number of positively charged protons in the nucleus equals the number of negatively charged electrons outside the nucleus. When an atom gains or loses electrons, ions are formed which are electrically charged. So atom is electrically neutral, but ions are charged particles which is formed when an atom gains or loses electrons. So here comes an example. First one is chlorine atom, which has got 17 protons, 17 electrons. Equal protons, equal electrons means it's a neutral atom. So when an electron is gained by a chlorine atom, extra charge is there. So chlorine becomes chloride ion. That time proton is not changed, but electron is gained. So electron number increases by 1. So now it has become a negatively charged ion, which is called chloride ion. Chloride ion has a single negative charge because there are 17 protons and 18 electrons. Charge difference of 1, minus 1. Magnesium atom, 12 protons, 12 electrons. It loses 2 electrons and forms magnesium ion. Mg becomes Mg2+. That means 2 electrons are lost. So 2 positive charges will be more than electrons. So that's why 12 protons, 10 electrons. So it gains 2 positive charge. Mg becomes Mg2+ ion. Now it's an ion. It's a positively charged ion. The next topic is isotopes. Atoms of the same element that have different number of neutrons are called isotopes. So this statement is very important. They are atoms of the same element, but they have different neutrons. That's called isotope. So here it's an example is shown. You can see these are the isotopes of hydrogen, protium, deuterium and tritium. In protium you can see 1 proton but 0 neutron. So if there is 1 proton, there will be 1 electron for sure. Then only it becomes a neutral atom. So the symbol is 1H1. Focus on the second one, deuterium. There is 1 proton and 1 neutron inside the nucleus and 1 electron. So the nucleon means mass number. Mass number is the proton number plus neutron number. So it has become 2. Symbol becomes 1H2. In the case of tritium, there is 2 neutrons and 1 protons. So it has become 1H3. So when you compare this, you can see the number of neutrons is varied here in protium, deuterium and tritium. Protium has no neutrons, deuterium has 1 neutron and tritium has 2 neutrons. So that's why when they differ in their neutrons and they are all atoms of the same element, hydrogen, that's why they are called isotopes. Isotopes of a particular element have the same chemical properties because they have same number of electrons. Electrons are not changing. Same electrons, same chemical properties. But they show different physical properties, slightly different physical properties, such as small differences in density or small differences in mass because they have different number of neutrons. So neutrons gives the differences in mass or density. So how to represent an element in the form of a chemical symbol? As you can see here, always we chose proton number at the bottom left and nucleon number at the top left. Symbol for the isotope of boron with 5 protons and 11 neutrons is written as 5B11. So 11 indicates the mass number or the nucleon number and 5 is the proton number. That's how you represent an element. The next subtopic is electrons, energy levels and atomic orbitals. The new topic is shells. It's a new keyword, shells. What are shells? They are otherwise called energy levels. So these are the spaces where you can see electrons outside the nucleus. So these energy levels are the spaces where you will see the electrons, and you can call that as energy levels or quantum shells. So these energy levels, quantum shells, are otherwise called principal quantum shells and represented by the symbol N. And they are numbered according to how far they are from the nucleus. The lowest shell, N equals 1, is closest to the nucleus. The next shell, next energy level or next quantum shell is N equals 2, is further out, and so on. The electrons in the quantum shells further away from the nucleus have more energy and are held less tightly to the nucleus. The arrangement of electrons in an atom is called its electronic structure or electronic configuration. So this is the arrangement of electrons. When you arrange electrons outside the nucleus, and that means it's called electronic configuration. So this arrangement is called electronic arrangement or electronic configuration. So now we will see what are electron orbitals. Each shell can be divided further into subshells. So this is labeled as S, P, D and F. So you have to remember one thing. The outside of the nucleus is the space where you can find the electrons. That space is called shell. And inside shell there are some regions where specifically you will see the electrons. Those specific region inside the shell is called subshell. These subshells are named as S, P, D and F, and each of the subshell has got its orbitals. So inside subshell you will see orbitals. That's a specific pointed region where you will find the electrons. So orbitals are seen inside subshells, subshell inside shells. So that's how. And each subshell can hold a specific number of orbitals. As you can see, S subshell, that's the first one. S subshell can hold 1 orbital. P subshell can hold 3 orbitals. Px, Py, Pz. D subshell 5 orbitals. F subshell 7 orbitals. So 1, 3, 5, 7. This is the orbital number of each subshell. Now, what about an orbital? How are the electrons located inside an orbital? Each orbital can hold a maximum number of 2 electrons. So the maximum number of electrons in each subshell are S. As I told before, S contains 1 orbital, and 1 orbital can hold a maximum of 2 electrons. So S subshell has a total of 2 electrons. Similarly, P has got 3 orbitals, and 1 orbital 2 electrons. So 3 times 2 it becomes 6 electrons. D subshell 5 orbitals, so 10 electrons. F subshell 7 orbitals, so 14 electrons. These subshells increase in energy as follows: S, P, D and F. So the lowest in energy is S, then P, then D, then F. The only exception to these rules is the 3D orbital, which has a slightly higher energy than the 4s orbital. So this is a point to be noted when it comes in the case of 3D and 4s. 3D has got slightly higher energy than 4s. Therefore, the 4s orbital is filled before the 3D orbital when you arrange the electrons or when you write the electronic configuration. You should follow this rule when it comes in the case of 3D and 4s. All the orbitals in the same subshell have same energy and are said to be degenerate. For example, all the orbitals in P, Px, Py, Pz are all equal in energy. Again, D has got 5 orbitals. All those 5 orbitals are equal in energy. They are said to be degenerate orbitals. But S is different in energy than P is different in energy than D is different in energy than F. Subshells differ in their energy, but in a subshell the orbitals are of same energy. That's what it's mentioned. You can see here the increasing energy levels. Quantum number or quantum shell 1, only one subshell, which is 1s. Quantum shell 2, you can see there are 2 orbitals, 2s and 2p. You can see S and P, so 2 subshells are there, S subshell and P subshell. And 3 subshells, 3s, 3p, 3d. And 4s, 4p, 4d. You can see like that, and 4f. So it's like that, it goes on. The number of shells gives you the number of subshell number, and subshell, from the subshell you can calculate the orbital number, and therefore the number of electrons can be calculated finally. And you should know the shapes of S and P orbitals only, no need of D and F. Only these 2 are mentioned in the syllabus, so we focus on S and P orbital shapes. S orbital is spherical in shape, as you can see here, and P orbitals are dumbbell in shape. This is a dumbbell shape. And s orbital, as you can see, please locate. In the p orbital, you can see the node. Node means it's a point where an electron cannot be located. So only electrons can be seen in the lobes, not at the node. More nodes means higher energy, less electron. So that's it. Please, you have to learn the shapes of these orbitals: px, py, pz. As you can see here, px means this is the lobe is along the x-axis. Py, the lobe is along the y-axis. Pz, the lobe is along the z-axis. That's how. Now this is what I mentioned a while ago, how to fill the shells and orbitals. You should follow this rule. This rule is called Aufbau principle. No need to study the rule and all, just you have to look at this, the filling up of subshells in the increasing order of their energy. The only exceptional case is 3d and 4s. 3d will be having higher energy than 4s. As you can see, you have to follow this rule. 1s, focus or follow the arrows. 1s, then 2s, then fill up 2p, then 3s, then go to 3p, then 4s. After 4s, go to 3d, 4p, 5s, then 4d, 5p, 6s. It goes on like that. So you have to follow the arrow. That's all. While filling the electrons in an in an atom. So here comes the examples how to fill up. Lithium 1s2, 2s1. How is that? Lithium is atomic number 3. So as you know, there are 3 electrons. So it goes, the first 2 electrons goes to the first orbital inside the first shell. So 1s indicates that it's a first shell and s subshell. And as you know, s subshell has got 1 orbital. It can hold 2 electrons maximum. So that's why 1s2. After 1s, there is no 1p, so you have to move to 2s. The second energy level is 2s. So from the total of 3 electrons, 2 is already in the first shell. Remaining 1 goes to the second shell, 2s1. So the next, beside that, one more you can see here how to fill up the electrons in the boxes. This boxes indicates the orbitals. Each orbital, you can see 1s subshell, you can see s subshell, again 2s subshell, p subshell. Inside p you can see 3 orbitals. So lithium, in the case of lithium, 1s2 to s1, the first 2 electrons goes to 1s. And please make a note that when you write, the electron spinning is in opposite directions. One electron spins clockwise, the other electron spins anti-clockwise. So you are supposed to put here the arrows in the opposite manner. One clockwise, another one anti-clockwise. So 2 here and 1 in the 2s. Beryllium 1s2, 2s2. So 2 in the 1s and 2 in the 2s. Boron 1s2, 2s2, 2p1. So that P has got 1 electron. Carbon, P has got 2 electrons. Finally, neon, P is fully filled. So make sure when you draw this, first P, one by one, you have to fill up all the P orbitals, then come and pair the second P. In the case of oxygen, as you can see here, 2p4. So all the P orbitals are having same energy. That means you have to fill each of the orbital with 1 electrons in the beginning. Then you can come and pair the second electron. That's how. So this is the element. These are the elements from calcium to zinc. Same electronic configuration. Here you have to notice one thing. After calcium is scandium. Scandium is 21. So after 3p comes 4s. That's the only thing you have to focus on, because 4s is lower in energy than 3d. So fill up the 4s first and then 3d1, like that. So scandium, titanium, vanadium, chromium. In the case of chromium, actually when you write, the configuration becomes 4s2, 3d4. So here there is an exception, and this I will talk about that. So chromium and copper, you can see these two are given a star here. That means these two are exceptional cases. We'll see that now. There are 2 main exceptions to electronic configuration. A completely full or half full d subshell is more stable than a partially filled d subshell. So an electron from the 4s orbital is excited to the 3d orbital. As you can see here, chromium is 3d5 4s1 or 4s1 3d5. In both the ways you can write. Either you can write, when you write 4s first, 3d5 also it's okay. Then 3d5 4s1 is also okay. But remember, filling is first goes to 4s. Only then you have to fill 3d. So when you fill up, actually it becomes 4s2 3d 4s2 3d4. But we are taking one electron from 4s2 and giving that, and has given that to 3d to make it 3d5, because 3d has the capacity to occupy 10 electrons maximum, 10 electrons. So the maximum 10 is more stable. That's called fully filled d sub level. Or if d is half of that, that means half of 10 is 5. So if d comes as d5 or d comes as d10, then that configuration is said to be more stable. So what we do is that in the case of chromium and copper, the configuration is becoming 3d4 and 4s2, because we are filling 4s2 first, 4s2 and 3d4. But we know that d is about to get filled, stable, about to be stable if one more electron is there in the d level. So what we do is that we take one electron from the outer shell. Outer shell is a fourth shell. That means from 4s, one electron is borrowed and given to d in order to make it d5. Then it becomes more stable, and it's called half-filled stability. In the case of copper also, when you write the configuration, it shows 4s2 and 3d9. But you borrow one and make it 3d10 4s1. And this state is called completely filled d orbital. These two are exceptions, exceptional cases when you write electronic configuration. So please remember these two. Now the next form of writing is shorthand electronic configuration. This is shorthand because we replace some of the configurations by an inert gas. So this configuration is also called noble gas configuration or inert gas configuration also. As you can see here, the first element, potassium, is K. Potassium is 19. So you have to look at the inert gas or noble gas which is coming just before 19. As you know, the noble gas is 18, which is argon. Argon is a noble gas just before 19. So until that you can write it as argon, and remaining one electron fill up to the next subshell, which is 4s1. That's how 4s1. Because the three orbitals are three periods has been filled there, so it's going to the fourth shell. 20 calcium, it goes to 4s2. So 18 argon is filled and it goes to the next one. 2 electrons goes to 4s2. When it comes to scandium, argon 18, and then we have got 19, 20, 21, 3 electrons. But remember, after 4s comes 3d. So after filling 4s2, it goes to 3d1. Because 4s is lesser in energy. So fill up 4s first, then comes 3d. So that's how it's been filled here. You can just have a look at here. This is called the inert gas configuration or shorthand electronic configuration or noble gas electronic configuration. Now, when it comes in the case of electronic configuration of ions, and you know, as we have already seen, ions are formed when atoms lose or gain electrons. Negative ions are formed by adding electrons to the outer subshell. Positive ions are formed by removing electrons from the outer subshell. Transition metals fill the 4s subshell before the 3d subshell, but lose electrons from the 4s first. So this is a point you have to note it. It's very important. When you fill in, you fill up the 4s first, then the 3d. But when you take away the electrons, when you lose electrons from an atom or an ion, you have to remove it from the 4s first. not from the 3D, because fourth shell is the outer shell. So removing always takes place from the outer shell. 3 is the inside one. Fourth shell is the outside. And also 4s subshell is lower in energy than 3D. So it's very easy to remove the electrons from the lower energy than the higher energy. So point to be noted, filling first 4s subshell, then 3D. Removing electrons from 4s first. So both filling and removing from the 4s subshell, not from the 3D. This is a point you have to remember. As you can see here, an example of an atom and an ion. Titanium atom. The configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d2, 4s2. And when the question is the configuration of titanium 2 positive ion, that means 2 electron has to be removed when you write the configuration. From where will you remove? That is removed from the outer shell, which is a lower subshell, which lower energy subshell is 4s. So remove the electrons from the 4s. Likewise, for chromium, the configuration is 3d5 4s1. Chromium 3 plus, remove 1 from 4s and then 2 from 3d. So it becomes 3d3. Chromium 3 plus becomes 1s2, 2s2, 2p6, 3s2, 3p6 and 3d3. So that's the configuration. The next subtopic is atomic and ionic radius. The atomic radius of an element is a measure of the size of an atom. It is half the distance between the two nuclei of two covalently bonded atoms of the same type. So when there is two covalently bonded atoms of same type, you take the distance from one nucleus to the other nucleus, and the radius is half of that, half the distance between the two nuclei of two covalently bonded atoms of the same type. And atomic radii show predictable patterns across a periodic table. They generally decrease across each period. Now the reason for that. The atomic radii decrease as you move across a period. As the atomic number increases, remember this point, there will be increased positive nuclear charge. But at the same time, extra electrons are added to the same shell, same principal quantum shell. The larger the nuclear charge, the greater the pull of the nuclei on the electrons, which results in smaller atoms. So as you can see here, when you move from left to right in a periodic table, the number of protons increases. That means the nuclear charge increases. When the number of protons increases, number of electrons also increases. But you have to notice a point. These electrons are getting added to the same shell because they are in the same period in a periodic table. Same shell. So all of these electrons will be attracted towards the nucleus. The pull of the nucleus will be more. So they attract more and pull the electrons towards the nucleus. Therefore, the size of the atom decreases. That means the atomic radii decrease across a period. Now the next one, atomic radii increase moving down a group. So here, there is an increased number of shells going down the group. They are in different periods. That means different shells. First shell, second shell, third shell, fourth shell. So even though the nuclear charge is increasing, the shell number is increasing. So the electrons in the inner shells repel the electrons in the outermost shells, shielding them from the positive nuclear charge. This weakens the pull of the nuclei on the electrons, resulting in larger atoms. That's how the size increases. So since there is shielding effect of the inner shells, the outer electrons are not attracted to the nucleus as before. So the size of the atom is more. A similar case with ionic radius. Let's see. The ionic radius of an element is a measure of the size of an ion. Ionic radii show predictable patterns. Look at the pattern. Ionic radii increase with increasing negative charge. Negative charge means more electrons. So more negative charge, more radii. More positive charge, less electron. So radii decreases. Ionic radii increase with increasing negative charge. Ionic radii decrease with increasing positive charge. That means cations are smaller in charge, anions are bigger in charge when compared to a neutral atom. Ions with negative charges are formed by atoms accepting extra electrons, while the nuclear charge remains the same. The outermost electrons are further away from the positively charged nucleus and are therefore held only weakly to the nucleus, which increases the ionic radius. The greater the negative charge, the larger the ionic radius. Positively charged ions are formed by atoms losing electrons. Nuclear charge remains the same, but there are now fewer electrons which undergo a greater electrostatic force of attraction to the nucleus, which decreases the ionic radius. The greater the positive charge, the smaller the ionic radius. So more positive, less electrons, so pull will be more, so the ionic radii will be lesser. The next subtopic is ionization energy. The ionization energy, or the first ionization energy, is the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous unipositive ions. It's measured in kilojoules per mole. So remember, it's the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous positive ions. It's measured in kilojoules per mole. Sodium, example, sodium giving 1 electron and forms sodium positive ion. Oxygen, all of them are in gaseous state. Oxygen gives 1 electron, forms oxygen positive ion. The state symbol G must be shown in the equation as everything has to be a gas. Ion form must have a charge of positive 1. Now comes the factors affecting ionization energy. First factor is nuclear charge. More protons in the nucleus means a greater nuclear charge and stronger. Therefore, attraction to the outer shell electrons will be stronger. And so the first ionization energy is greater. So remember, more nuclear charge, stronger attraction to the outer shell electrons. So more ionization energy is required. Second factor, atomic radius. Larger atomic radius means weaker attraction between the positive nucleus and negative electrons. So first ionization energy is lower. Larger atomic radius, lower ionization energy. Third factor, electron shielding. More electron shells means more electron shielding, so weaker attraction between outer shell electrons and nucleus. So first ionization energy is lower. So these are the factors affecting ionization energy. The first ionization energy increases across a period. This is because although electron shielding remains the same, nuclear charge increases, which draws the outer shell electrons inwards, causing a slight decrease in atomic radius. This means more energy is required to remove an outer shell electron as it is attracted more strongly to the nucleus. Exceptions are there in period 2. These exceptions are present in period 3 for the same reasons. So let's see. Between groups 2 and group 3, electrons start to be added to a 2p orbital rather than 2s. And as you know, 2p is having slightly higher energy level than 2s. So this electron is found slightly further from the nucleus, meaning it can be removed more easily. So lesser energy required. So remember one thing, if the electrons are in 2p, so they are further away from the nucleus, That means the attraction power is lesser, so you can easily remove an electron. That means ionization energy will be lesser. Similarly, between groups 5 and 6, electrons start to pair in the 2p orbitals. The paired electrons, when they are paired, there will be a force of repulsion because both are negatively charged, so they repel each other. This repulsive force allows an electron to be removed with less energy than expected. So already they are ready to repel. So if you provide some more ionization energy, that means a lesser or a fewer amount of ionization energy is required to remove an electron from the paired state. First, ionization energy decreases down the group. Because although nuclear charge increases, there is electron shielding also here. Their atomic radius and electron shielding also increase, meaning less energy is required to remove. That means ionization energy is lesser. And what do you mean by successive ionization energies? Successive ionization energies involve removing 1 mole of electrons from 1 mole of gaseous ions. If you remove from 1 mole of gaseous atoms, it's called first ionization energy. If you remove from the gaseous ion, then the next ionization energies are called successive ionization energy. For example, third ionization energy of potassium would involve removing 1 electron from K2 plus to form K3 plus. You can see the example given here in details. First 3 ionization energies of aluminium are shown below. Aluminium, first gaseous atom, it's when to remove 1 electron and form Al plus, it requires 577 kilojoules per mole of energy. That's called the first ionization energy. Now aluminium has become aluminium unipositive ion. So from the unipositive ion, if you want to remove 1 more electron, it becomes aluminium 2 plus, and you need to provide second ionization energy, which is called the successive ionization energy, and that is much greater, 1820, because already it's in the unipositive state. From the positive species, removing an electron is very difficult. That's why more energy is required. Likewise, in the case of aluminium 2 plus, giving away 1 electron to form aluminium 3 plus, more amount of ionization energy is required. That's given as 2740 kilojoules per mole, which is much more greater than the first and second. So therefore, successive ionization energies increase because atomic radius decreases and there is greater attraction between outer shell electrons and the nucleus. This is a kind of question you get. A large jump between successive ionization energies indicates which group an element is in. So you will be asked to find out, the data will be provided like this, and you are asked to find out which group this element belongs to. So here is the clue for that. Here successive ionization energies for an element is shown below. First one 801, second, third, fourth and fifth. The large jump between the third and fourth ionization energy, there is a large jump as you can see here. Third is 3660 only. Fourth is 25,000. So it's much greater than the third one. So there is a large jump between the third and the fourth ionization energy, which shows that there are 3 electrons that are relatively easy to remove than the fourth one, which requires a lot more energy to remove. This gives you an idea that there are 3 electrons in the outer shell. This means that the element is in group 3 because it's a 3 electron in the outer shell. Because from the third to the fourth there is a large jump in the ionization energy. So this element is in group 3. There are 5 ionization energies for this element, so it has total of 5 electrons. An element with 5 electrons in group 3 is boron. So there are total 5 electrons because there are 5 ionization energies. So the element in group 3 with 5 electrons is boron. So this is how you are supposed to find out the elements in a periodic table. How many elements, or which element, which is that particular element. That's how. So ionization energy helps us to decide the element in the periodic table, or locate the element in the periodic table. So that's all for this chapter. Thank you so much for watching this video.